Okay, good morning all. Hope my screen is visible. Okay, okay. So screen is visible and I am audible too. So let us start till the people join what we have seen last time. We were discussing about the transistor characteristics, transfer characteristics. So you found over here is that whenever you give the input voltage more than zero point 0.5 or you can say between 0.5 to 0.7 volt, then you can find that the characteristic seems to be linear. The curve seems to be linear. It look like a linear curve. But suppose if you give more than 0.7 volt, in that condition, the current value becomes too large and the voltage value is quite low. And similarly, when you give a voltage less than 0.5, in that condition, the current is too low and the voltage is at maximum, which is VCC. So transistor is operating in three different modes. When the input voltage is less than 0.4 to 0.5 volt, it is cut off. If the input voltage lies between 0.5 to 0.7, it is active. And if the input voltage is more than 0.7 and subsequently higher, then it will be going under saturation. So it is this three mode that is important for us. And now we are focusing on the active mode, that when the voltage is between 0.5 to 0.7, then how a transistor can operate as a amplifier. Now, as we have shown over here, that there is one point, there is one midpoint, rather you would say, which is known as the bias point. That point is known as quiescent point or a standstill point. Now, this Q point is the point which is telling us the operating voltage and the operating current of the transistor. So operating voltage and operating current is basically nothing but the Q point of the transistor, which is a stable point. That point will not vary with the time. That will remain as a stable one. And there are various possibilities, right? So the possibilities that we have seen, if you select a Q point at three different locations. So see, in the same curve, we have seen that if I take position 1, if I take position 2, and if I take position 3, in that condition, only position 1 is appropriate. Because at position 1, for a small input, you see, for a small input between 0.5 to 0.7, you can get large output. So you can cover the range or you can have a full waveform at your output. But on the contrary, if you select at 0.2 or 0.3, in that condition, your output on one side it will be maximum, on one side it will be very less, and on the vice versa on either 0.2 or 0.3. So the Q point is selected in such a way that your input signal and your output signal should have sufficient swing. Swing means the oscillation at the upper side, oscillation at the lower side in positive cycle as well as negative cycle. It should be equal. If you select any other point, something like 2 and 3, in that condition, maybe the positive oscillation is higher, negative oscillation is smaller, or in negative oscillation is higher, positive oscillation is smaller. So that we have to keep in mind. So Q point is basically the DC point, which we would like to change when we establish the DC condition in a circuit. Then we have derived this output and input relationship, and we found that the common emitter amplifier circuit, what we have kept over here, it is following exponential series. You see that e to the power x, e to the power delta vi by delta vt. So it follows the exponential series, and we have derived and found the gain formulas and all. But here the condition is that only we would like to consider the first term, delta vi by delta vt. We would like to neglect the higher order terms, that square, cube, power 4, power 5 and all. That I can only neglect if this condition is fulfilled. Delta vi should be much smaller than vt. At room temperature, we know vt is 25 to 26 millivolt. So the input signal that I am supposed to give to the amplifier should be quite a small compared to VT. This is one of the condition to get rid of higher order terms. And then these are the gain formulas what we have derived. Even in laboratory also these formulas are equally valid. So Q point discussion that. Then this is what we were discussing. Now to establish that Q point, how to establish a proper Q point? Now that is the first question, because unless and until you have a proper Q point, you cannot operate the transistor as an amplifier. So the very first exercise that one has to do is to bias the transistor. आपको transistor को bias करना पड़ेगा. Now how do we bias? There are various techniques for it. So we start with one of the technique. So as I told you last time, that I start with one example, and during the example only I will keep on explaining you the advantages and disadvantages of a particular technique, and we find a better solution. So we taken this data that there is some leakage current which is provided, alpha is provided, and the question is you have to bias the transistor such that the emitter current should be 1 milliampere, collector emitter voltage should be 5 milliampere, sorry 5 volt, and the supply voltage is 10. So we have drawn the circuit, we have solved the circuit, and we found that RC is 5.025 kilo ohm. Once we found this RC, then we would like to find out the input voltage, that how much input I should give so that the emitter current is 1 milliampere, how much base emitter voltage one should give. So we have put this in the data, that equation, Shockley's equation. We have solved that equation. So we found that the base emitter voltage should be 0.631 volt. So now what is the conclusion? Conclusion is, in a given circuit, if I can give a DC voltage of 0.631 between base and emitter, then there is a guarantee that I can get emitter current of 1 milliampere. And if the emitter current is 1 milliampere, then all voltages and things which were mentioned in the data will remain as it is. But then there is a question, how to get this 0.631 volt? That's a very important question. So the solution we started with, the first solution we thought of that, okay, let us take a battery whose voltage is 0.631 volt. But as I told you last time, this is not a good solution, because battery voltage will never remain constant throughout the time period. Let us say today it is 0.631, tomorrow it will be 0.630, then 0.629 or anything. So it is keep on fluctuating. Now what is the problem? If the battery voltage, even if it is fluctuates by 0.1 or 0.01, the emitter current greatly fluctuates. Why? Because the base emitter voltage, which is 0.631, and the emitter current is related with the exponential relationship. The equation is in front of you. So a slight variation in VBE will take huge variation in emitter current. So again, the things are disturbed in your circuit if your battery voltage will not remain steady at 0.631, right? So this taking a battery and putting it over there is not a good solution. So we ruled out that solution. So now second question is, okay, I don't want to use battery, but somehow I want 0.631 volt. So let us say how I get that 0.631 volt. So the second solution we thought is this, that I know the alpha, so I found the beta. I found the beta, so I got base current, and we got the base current of 5 microampere. So now I know that if I can have a base current of 5 microampere, then automatically my emitter current will be 1 milliampere, because base current multiplied by beta plus 1 is eventually emitter current. So I can have that kind of situation. So now this is slightly better solution than what the battery option we have used, that now you have to fix some base current. So now the question is how to fix that base current, because if the base current is 5 micro, then only the emitter current will be 1 milli for this transistor. Then this is the solution, that okay, we have taken the same 10 volt battery जो VCC का supply हमने use किया है. We have put one resistor called RB, and then I wrote Kirchhoff's voltage law in the base emitter loop. So the equation is in front of you, and we found it for RB. So RB comes to be 1.87 milliohm. So if the voltage is 10 volt, if the RB is 1.87 milliohm, then the base current will be 5 microampere. If the base current is 5 microampere, then the emitter current will be 1 milliampere. So this is another solution, that now you are relying on some external resistance called RB, but now you got an advantage that you don't have to have a battery. आपको बैटरी की जरूरत नहीं है 0.631 वोल्ट की, वो अपने आप यहाँ पे क्रिएट हो जाएगा. So you have this kind of situation. But then there are certain drawbacks for this technique also in terms of stability. One of the problem is that you want, suppose let's say today you have put a transistor X. Yes, it is 1.87 mega, no? Yes, it is 1.87 mega ohm. Okay, so now this is also not good because let us say you want to replace the transistor for whatsoever reason. Let us say your circuit is not working and you found that there is some damage to the transistor. You still want to run your amplifier. So what you do, you replace your transistor with the new one. Your old transistor was 2N2222. Now your new transistor is BC547. So again, there is a problem that the beta of both the transistors will not remain same. And you know that in this equation, your emitter current is beta plus 1 into IB. तो आपका IB तो फिक्स हो गया, बट आपका बीटा इटसेल्फ इज अ फ्लक्चुएटिंग फैक्टर. बीटा ट्रांजिस्टर चेंज होने से भी चेंज हो जाता है. इवन इफ द ऑपरेटिंग कंडीशन चेंजेस, टेम्परेचर चेंजेस, योर बीटा इज कीप ऑन चेंजिंग. दैट मीन्स this is still not good technique to go with that, because emitter current is very sensitive to the beta variation. Beta is a temperature dependent quantity also. So that means IBQ को फिक्स करके IE को फिक्स करना इज नॉट अ गुड चॉइस. दिस मे बी वन ऑफ द ऑप्शन कि हाँ ठीक है, चलो IB को हमने कुछ फिक्स कर दिया और मुझे कुछ IE मिल गया, ठीक है, थोड़ा काम चल रहा है, बट स्टिल इट इज नॉट अ गुड सॉल्यूशन. सो व्हाट इज द गुड सॉल्यूशन? Good solution is you straight away target emitter current only. Why to rely on someone else? Straight away start working on the emitter current itself. So what you do, you fix the emitter current at 1 milliampere directly. So if the emitter current is 1 milliampere and if it remain fixed, then automatically collector current and base current will adjust themselves. वो अपने आप अपने को एडजस्ट कर लेंगे. आपको उसके लिए कोई चिंता करने की जरूरत नहीं है. You don't have to worry about it. Simply emitter current you target. So if you target the emitter current, then this is the situation. तो हमने यहाँ पे क्या सर्किट लिया है? The circuit what we have considered is something like this, that I will ground the base. मैंने base को ground कर दिया. If I ground the base, then the emitter voltage will be minus 0.631. Emitter current is minus, emitter voltage is minus 0.631. Now I want to fix the current. तो देखो, अगर आपके पास वोल्टेज है, आपको कुछ करंट फिक्स करना है, देन विदाउट रेजिस्टर यू कैन नॉट फिक्स द करंट. दैट इज द वेरी थंब रूल, लाइक ओम्स लॉ. ओम्स लॉ इज द रिलेशनशिप बिटवीन वोल्टेज, करंट एंड रेजिस्टर. आपके पास एमीटर पे वोल्टेज है माइनस 0.631. यू वांट एमीटर करंट टू बी 1 मिली एम्पियर. सो इन दैट कंडीशन यू हैव टू हैव रेजिस्टर. सो नाउ यू हैव टू इंसर्ट वन एक्सटर्नल रेजिस्टर कॉल्ड कैपिटल RE in the emitter branch, and then now you use dual supply because you want emitter current to let us say fix at 1 milliampere. So in this circuit, if you apply Kirchhoff's voltage law, so you found that capital RE is 9.369 kilo ohm. So now what you have done, you have fixed up the emitter current, and by fixing the emitter current, now you say that base and collector will adjust themselves, no problem. But here there are two problems. Here there are two problems. What are those problems? The problems are, yes, one of the problem is this circuit what you see, it doesn't look like common emitter, it look like common base, right? So whatever the advantages which are there with common emitter are not fully available with this circuit right now. So we want some solution for that. That is one thing. So now we would like to focus to solve this problem. कि circuit number 3 is better than 2, 2 is better than 1. So now we would like to stick to this circuit. We would like to stick to this circuit, but at the same time, we would like to modify this circuit in such a way that this circuit should work like a common emitter. We want some modification in this circuit by still retaining their advantages. उसका advantage हमें यहाँ पे दिख रहा है कि if I take one external resistance capital RE, I can fix the emitter current, and and another disadvantage is I need another supply. In previous two circuits, we don't require minus 10 volt supply. Only one supply was sufficient, 10 volt. But in this circuit, this is another disadvantage. One disadvantage is that this circuit looks like a common base. Second disadvantage is you need another minus 10 volt supply. So these are the two disadvantages. Other than that, this circuit is very appropriate. So now we would like to remove these two disadvantages. That I don't want to use dual supply. That is one of the option with me. And second is I want to convert my circuit again with the common emitter. Again, I have to bring the common emitter into the picture, right? So that is what now I would like to go with. Now in this circuit, see in this circuit, what important thing is, if you see the emitter current equation, अगर आप emitter current का अगर इसमें मुझे equation लिखना है तो how do I write? In the same circuit, now let me go to the writing pad. Okay, now in the same circuit, if I want to write the emitter current equation, हमारा circuit ऐसा है. This is how the circuit is. Minus 10. This is grounded. This is VBE Q. Let us say this is VEE. This is capital RE. This is emitter current IE. Right? So I can write IE is VEE minus VBE. या फिर okay, let me write in other proper way. Confusion नहीं होना चाहिए. This potential minus this potential divided by RE is IE. So now if you see the top potential is minus VBEQ क्योंकि base को ground कर दिया है. तो emitter is at minus VBEQ. This is minus VEE. This is minus VEE because it is 10. So VEE is 10, but minus VEE is minus 10. That's how we will follow. Divided by RE. So now IE is nothing but VEE minus VBEQ divided by RE. This is IE. So now I can get IC. What is IC? IC is alpha times IE. So what is IE? Same. VEE minus VBEQ divided by RE. Now what is the advantage of this equation? The advantage is alpha is not sensitive. Alpha is not sensitive, so current remain constant. Now why we write such thing? Because suppose if I take alpha equal to 0.9 and another option I take alpha is equal to 0.995. So in both the case, I can say that I am still near to 1. Even if the alpha changes from 0.9 to 0.995, I can say if my emitter current was 1 milliampere, then my collector current is 0.99 milliampere. So it is still approximately 1 milliampere. And in second case, it is still 0.995 milliampere. So I am near to that only. But for this case, if I write that what is the beta? If alpha is 0.99, then the beta will be 100. And if I have alpha equal to 0.995, then beta will be 200. So now you see the variation. You see the problem with beta. 0.005 variation in alpha leads 100 units of variation in beta. So in your equation, if the beta comes, then the circuit is unstable. But in this circuit, if you see, here we don't have anywhere in a beta. ये वाली सर्किट में कहीं पे भी बीटा नहीं है. We have collector current with alpha relationship, and alpha is not sensitive parameter because alpha 0.99 से 0.995 भी change होगा, but still we are very near to 1. However, when you see the beta variation, मतलब जो base current को fix करने वाला जो circuit था, if any variation in that, there is a huge variation in current, right? So that is why we should not rely on beta parameter, we should rely on alpha parameter. हमारी circuit ऐसी होनी चाहिए that we compute the parameters using alpha, not using beta. That is what is the requirement. So I just summarize very quickly. First option was use a battery, but we know it is not good. Second, use RB, fix IB, get IC and IE. This is also not good. Why it is not good? Because of the beta. Why it is not good? Because of the beta. और बीटा का प्रॉब्लम मैंने ऊपर लिख ही दिया है कि बीटा में ह्यूज वेरिएशन आता है इफ देयर इज अ स्मॉल वेरिएशन. सो टेम्परेचर की वजह से भी बीटा चेंज हो जाता है. व्हेन यू रिप्लेस द ट्रांजिस्टर देन आल्सो द बीटा चेंजेस. इवन इफ द ऑपरेटिंग करंट चेंजेस देन आल्सो बीटा चेंजेस. सो दैट इज नॉट देयर. देन थर्ड ऑप्शन, यूज RE, fix IE directly. This is good, but the problems we know. Problem is minus VEE additional supply and common base configuration. तो अभी इसको हमें सॉल्व करना है. Now we would like to solve the problem. So let us target the first one. Let us target the first problem. ये जो एडिशनल सप्लाई का प्रॉब्लम है पहले उसको टारगेट करते हैं, बाद में ये कॉमन बेस वाले प्रॉब्लम को टारगेट करेंगे. सो लेट अस टारगेट द फर्स्ट वन. द क्वेश्चन इज हाउ टू गेट रीड ऑफ ड्यूअल सप्लाई. मुझे दो सप्लाई यूज नहीं करने हैं, मुझे सिर्फ एक ही सप्लाई यूज करना है. देन हाउ डू आई गो विद दैट? एंड in this, suppose RB and RE both are there. Now we would like to make a circuit where there is RE in emitter circuit, there is a RB in base circuit, and I don't want to use dual supply. तो सबसे पहले तो जो प्रॉब्लम है वो सर्किट ड्रॉ करते हैं. आपका जो सर्किट है वो ऐसा है. योर सर्किट इज दिस, राइट? देखो मैंने ये आपका VEE ड्रॉ किया. दिस इज द VEE विच आई हैव ड्रॉन. ये है आपका RC, ये है आपका VCC. देखो मैं सिर्फ एक अलग तरीके से ड्रॉ कर रहा हूँ, बाकी सब कुछ सेम है. सो डोंट वरी, सर्किट इज स्टिल सेम, सिर्फ ड्रॉ करने का तरीका थोड़ा अलग है टू एक्सप्लेन. राइट, अभी आपका सर्किट ऐसा कुछ है, राइट? RC, VCC, VEE, capital RE, right? So all agree, this is your circuit number 3. जो हमने पहले देखा था वही ये सर्किट है. मैंने कुछ नया नहीं लिया है, बेस को ग्राउंड ही रखा है. एमीटर के सीरीज में कैपिटल आर ई लगाया है, एमीटर को एक नेगेटिव सप्लाई दिया है, कलेक्टर को वीसीसी दिया है वाया आरसी। सो सब कुछ सेम है, मैंने कुछ भी चेंज नहीं किया है। I hope everyone agrees with that, let's say, statement. The circuit still remain as it is. Now, solution we are interested to find. तो सबसे पहले क्या करते हैं, let me take this circuit as a copy. मैं इसका एक कॉपी ले लेता हूँ, यहीं पे उसको साइड में ऐड कर देता हूँ, so that because I want to compare. मुझे इसको कंपेयर करना है, इसलिए मैंने इसको यहाँ पे रख दिया। ओके, सबसे पहला स्टेप क्या करेंगे? सबसे पहला स्टेप, if I shift this, if I shift this from emitter branch to base branch, सपोज मैं इसको यहां से शिफ्ट करके अच्छा वो यहां पे नहीं है, सपोज मैं इसको शिफ्ट करके यहां पे ऐसे कनेक्ट कर दूं, लेट अस से आई एम शिफ्टिंग दिस, तो देखो इसमें हुआ क्या, जो सप्लाई एमीटर में था उसको मैंने शिफ्ट करके बेस में कर दिया। अभी भी देखो बेस में क्या है, ये जो पॉजिटिव था वो वाया बेस को ही कनेक्टेड था, नेगेटिव था वो एमीटर को कनेक्टेड था। अभी भी मीनिंग वही रहा, मीनिंग चेंज नहीं हुआ है, मीनिंग इज स्टिल सेम, मीनिंग इज स्टिल सेम। तो circuit remains same if you shift VEE to base. If you shift this VEE to base circuit, still the bias is stable. I can write that bias is still stable, but now the VEE value will not be VCC value. हमारे सर्किट में क्या था, हमारे सर्किट में ये वाली सर्किट में यहाँ पे जो VCC था, यहाँ पे जो VCC था, दिस इज RC एंड दिस इज VCC. सो मैग्नीट्यूड वाइज VCC वाज सेम एज VEE. एक +10 था, एक -10 था, तो मैग्नीट्यूड वाइज दोनों 10 थे इन दिस सर्किट। यही सर्किट है, उसी को हमने अलग तरीके से यहाँ पे ड्रॉ किया, and then we found कि okay, let me shift this VEE from emitter to base and let us see is there any effect. So मीनिंग कोई चेंज नहीं हुआ है, मीनिंग अभी भी वही है, सर्किट अभी भी वैसे ही काम कर रहा है, बट नाउ द VEE विल नॉट रिमेन VCC, द वैल्यू विच आई शिफ्ट। तो अभी ये जो ब्लैक कलर का जो सप्लाई है यहाँ पे जो मैंने बेस पे शिफ्ट किया है फ्रॉम एमीटर, पहले मैंने एमीटर में रखा था तब उसका वैल्यू था -10. Now if I shift it to base with this polarity, then obviously our answer is it will be +10. So if it is +10, suppose if it is +10, then why this problem occurs? So the problem occurs because हमारा जो एग्जाम्पल है उसमें हमने VCC क्या लिया है, we have taken VCC as +10 volt, RC is 5K, collector current is 1 milliampere. So under that case, this voltage is what? This voltage is 5 volt. We know VCC minus ICRC, this voltage is 5. Now, if this voltage is 5 and if this VEE is also same as VCC, so that means it becomes 10. Now you see, base is at 10 volt, collector is at 5 volt. And what is the foremost condition that we have to follow? कलेक्टर बेस वोल्टेज मस्ट बी रिवर्स बायस। तो अभी तो ये क्या हो गया, कलेक्टर शुड ऑलवेज बी हायर देन द बेस पोटेंशियल, कलेक्टर का पोटेंशियल हमेशा बेस से हायर होना चाहिए, बट यहाँ पे वो कंडीशन वायलेट हुआ, यहाँ पे बेस का पोटेंशियल कलेक्टर से ज्यादा हो गया। सो बिकॉज ऑफ दैट नाउ व्हाट हैपेंड, द ट्रांजिस्टर एंटर्स इनटू सैचुरेशन। अभी ये फॉरवर्ड बायस में आ गया बेस कलेक्टर जंक्शन, सो ये भी फॉरवर्ड बायस, नीचे वाला जंक्शन भी फॉरवर्ड बायस, so it is like a saturation kind of situation. So to avoid that situation, what condition we have to follow? I can't take the same magnitude as VCC, that is one thing. So VEE value which is shifted on the base can't be the same 10 volt value, but it should be less. How much less? It should be less by a factor VCC minus ICRC. हमें पता है VCC माइनस ICRC कितना है, 5 वोल्ट. मतलब मुझे जो यहाँ पे VEE लेना पड़ेगा वो 5 वोल्ट से कम लेना पड़ेगा. The VEE battery which I am putting in a base circuit should have a magnitude less than VCC minus ICRC. Then and then base collector junction will remain in reverse bias condition. तभी वो रिवर्स बायस में रहेगा, अदरवाइज रिवर्स बायस का वायलेशन होगा. तो ये तो कभी भी नहीं होना चाहिए. सो नाउ यू गेट वन आइडिया कि मैं एमीटर में से बेस में किसी को ट्रांसफर यहाँ पे करता हूँ. दैट इज पॉसिबल, आई कैन डू लाइक दिस, बट द कंडीशन दैट आई हैव टू फॉलो कि आई हैव टू यूज सम वोल्टेज सप्लाई इन बेस हुज मैग्नीट्यूड इज लेस देन VCC, राइट. सो उसका यहाँ पे मुझे मैग्नीट्यूड कम चाहिए. So now what is the solution? Solution is use VCC to derive new VEE. I am now giving name new because I know old VEE is 10 which can't be used. So now I want to derive new VEE, but that VEE I should not use in a separate battery. Suppose मुझे 5 वोल्ट की जरूरत है तो मैं 5 वोल्ट का बैटरी नहीं लगाऊंगा. Why 5 वोल्ट का बैटरी नहीं लगाऊंगा? Because I already have one supply who's called VCC and whose value is 10, whose magnitude is higher than what I need. So that is one good sign कि मेरे पास एक वोल्टेज सोर्स है जिसका वोल्टेज रेटिंग है that is higher than what I need. So then I can write this statement. Let us use VCC to derive this new VEE. So new VEE we would like to use. So if I want to use this, then how we can proceed? So that tells this process is now inviting fourth circuit that is called voltage divider bias. Because I want a voltage which is less than VCC, so I can use one voltage divider circuit. तो मैं voltage divider circuit use कर सकता हूँ. तो circuit में मैं क्या करूँगा? We have our original circuit as it is. तो मैं यहाँ पे RE लिख देता हूँ. अभी इसको हमने शिफ्ट कर दिया है. यहाँ पे है RC, यहाँ पे है आपका VCC. सो यहाँ पे कोई चेंज नहीं है. This is as usual, no change. Now I want here some voltage. मुझे यहाँ पे एक वोल्टेज चाहिए. That voltage I want, now I am giving new name as VBB. अभी मैं इसको नया नाम देता हूँ VBB, क्योंकि हम नाम का कन्वेंशन वैसे ही फॉलो कर रहे हैं. कलेक्टर में है तो VCC, एमीटर में है तो VEE, बेस में है तो VBB. तो आई वांट सम VBB. मुझे कुछ VBB लाना है. VBB मैं कहां से ला रहा हूं? आई एम गेटिंग VBB फ्रॉम VCC. फ्रॉम VCC आई वांट टू डिराइव VBB. सो हाउ डू आई गो विद दैट? सो द सॉल्यूशन इज दिस कि आप VCC में से एक एक्स्ट्रा ब्रांच कनेक्ट करो विथ वन वोल्टेज डिवाइडर नेटवर्क. With one voltage divider network, and that voltage divider network is, let us say, R2 and R1, जो हमने लैब में भी देखा था. हमने डायरेक्टली इसको ले लिया था, बट इसका इवोल्यूशन कहाँ से हुआ? यहाँ से हुआ. ये नीड यहाँ से अराइज हुई है कि मुझे ऐसा एक ग्रीन कलर का ब्रांच चाहिए. आई वॉन्ट दिस VBB ब्रांच. तो मैं उसको कहाँ से लाऊंगा? आई विल गेट डायरेक्टली फ्रॉम दिस R1 R2 let's say division. So for that क्या करेंगे? You want this VCC. आपको ये पॉइंट पे कुछ वोल्टेज चाहिए. So that voltage now you know. This voltage is VCC divided by R1 plus R2 into R1. Voltage divider rule. Simple voltage divider rule we have applied over here. So that voltage is known as Thevenin's voltage, and Thevenin's voltage is nothing but R1 divided by R1 plus R2 into VCC, and this we give a name as VBB. इसको हम VBB का नाम देंगे. We have created this circuit, and then I have, but see, my requirement was just to get VBB, but I'm not only getting VBB. Along with VBB, I am getting one series resistance also, because of this R1 R2 voltage divider network, that is called RTH, and let us say this we give name as RB. So I want VBB, I got VBB, but along with VBB I got one more additional resistance because of this effect of Thevenin's resistance. So I have, so what you can interpret out of this, to get this green color I need this blue color circuit. To get the green color VBB supply, I obtain that green color VBB supply through this blue color R1 R2 voltage divider biasing circuit. So from this you will get that. So now this circuit you can redraw. ये सर्किट को आप redraw करोगे तो how your circuit will look like? Your circuit will be very simple now. You have that original RE, this, you have VCC here, you have VCC, you have RC, and then you have this situation. This is the situation. So this is VBB, this is RB, and ओरिजिनल जो पहले का सर्किट था वो तो एज इट इज था. सो टू गेट दिस सर्किट, आपका सर्किट कॉन्फ़िगरेशन कैसा दिखेगा? द सर्किट कॉन्फ़िगरेशन विल लुक लाइक दिस. तो आपका सर्किट एक्चुअली ऐसा है. दिस इज योर सर्किट, RE, ग्राउंड, RC, VCC, R2, R2, R1, and this. So this can be equivalently draw as this. जो मैंने आगे ड्रॉ किया है वो RB equal to RTH. This is VTH equal to VBB, and then you have your own original transistor. जो बाकी का सर्किट है वो as it is है, उसको चेंज नहीं करना है. This is what your voltage divider biasing circuit. This is what is your voltage divider biasing circuit. तो देखो यहाँ पे जो हमारा फर्स्ट प्रॉब्लम था वो सॉल्व हो गया. फर्स्ट प्रॉब्लम क्या था? ड्यूअल सप्लाई से रीड लेना. दैट्स व्हाट वी हैव रिटन हियर. नो, मुझे ड्यूअल सप्लाई हटाना है. तो फर्स्ट गोल इज नाउ फुलफिल. मैंने फर्स्ट गोल को फुलफिल कर दिया कि नाउ इन माय सर्किट देयर इज ओनली वन सप्लाई. सी दिस इज माय फाइनल सर्किट. ये जो लेफ्ट साइड वाला सर्किट है, this circuit is the final. It is the actual circuit. Actual circuit look. Actual circuit बस आपका यही है. तो इसमें देखो एक ही सप्लाई है. And because of that, you analyze the circuit, you will get this VBB and RBB or RB. So first goal is now fulfilled. कि आपका ड्यूअल सप्लाई का जो प्रॉब्लम था वो अभी निकल गया. Now you don't need dual supply, right? So that problem is now solved. सेकेंड प्रॉब्लम को अभी थोड़ी देर के बाद टारगेट करते हैं. दैट आई वांट टू कन्वर्ट फ्रॉम कॉमन बेस टू कॉमन एमीटर. बट लेट अस फर्स्ट ऑफ ऑल एनालाइज दिस सर्किट. इसका जो मैंने इक्विवेलेंट यहाँ पे ड्रॉ किया है वो हम कैसे इंटरप्रेट करेंगे इसको. सो नाउ हियर दिस इज VBEQ, DC voltage जो है 0.631 volt वाला, everything is there. Now here the RB should be small. Ideally तो मुझे RB was not at all required. I only want VBB, but I can't only get VBB. I get RB. But now what is the advantage? The value of RB is in my hand. Why? Because it depends on R1 R2 combination. So if I select the R1 R2 combination in such a way that the RB value is very small, then I can fulfill this criteria and I can get almost a voltage like VBB. So this is what is required over here. Now, what is the voltage drop across RB? Let us say what is VRB. So VRB, let us say this current is IB, then VRB is IB into RB. The voltage drop across RB is IB into RB. Now, let us say this voltage. This voltage is VB, base to ground. ये जो ग्रीन कलर का मैंने यहाँ पे ड्रॉ किया विथ प्लस माइनस पोलैरिटी, दैट इज कॉल्ड VB. So if I write VB, what is VB? VB is nothing but VBB minus IBRB. I can straight away write like this. VBB minus IBRB drop is nothing but the VB voltage, right? So I can write over here. But this VB is also on right side. अभी तो देखो हमने ये left side का इक्वेशन लिखा that VBB minus IBRB. I can also write that VB is what? VBEQ plus IERE. यहाँ पे भी IE करंट जो जाता है तो IERE ड्रॉप होगा तो वो प्लस माइनस डायरेक्शन में होगा. तो VBEQ plus IERE ड्रॉप is also nothing but VB. So now I have two equations of VB, equation 1 and equation 2. Let us equate them. So what we get? If we equate them, then we get VBEQ plus IERE equal to VBB minus IBRB. Now, IBRB drop should be negligible. IBRB drop should be negligible compared to whom? Compared to IERE. So the condition what we follow is this, that IBRB drop should be much smaller than IERE drop. It should be IERE drop. Let us take this equation on the next page. I take this equation here. Okay. Now let us solve this equation further. What is IB in terms of IE? IE divided by beta plus 1 into RB should be less than IERE. Okay. So IE get cancelled. So now you got RB. So RB should be selected in such a way that RB should be less than RE into beta plus 1. This is the condition for the selection of R1 and R2. You can't select R1 and R2 arbitrarily. There is a condition to be followed. This is rule. This is the rule that is to be followed, that you will select RB such that it should be at least 10 times smaller than the RE into beta plus 1 product. But this task is very easy. Why this task is very easy? Because beta is relatively higher number. So beta is 199, suppose if I consider. So beta plus 1 factor is 200. Even if the RE is 1 kilo ohm, then the right side is 200 kilo ohm. So you want to select R1 R2 parallel combination whose value is less than 200 kilo ohm, at least 10 times less. That means 20 kilo ohm. तो मुझे RB ऐसा select करना है, और rather in other words I would say I have to select R1 and R2 such that the equivalent combination, the parallel combination should be less than 20K. Just an example I gave. So this is what you are supposed to do. So this is the rule. So in that condition, I can neglect this IBRB drop. So let us say this IB/RB drop is now negligible, then what I can write about emitter current? The emitter current is VBB minus VBEQ divided by RE. तो ये हुआ आपका, sorry, this is the emitter current from this equation, because I have neglected IB/RB drop. IB/RB drop को neglect किया because I understand that that condition is fulfilled. So under that condition now what happened? IE हमारा आया VBB minus VBEQ divided by RE. This is what the emitter current equation we got after neglecting IB/RB drop, right? So I got this equation. If you recall the original equation of IE, original equation of IE was VEE minus VBEQ divided by RE from dual supply concept. So now I can say that by observing these two equations, I am still getting the same emitter current what I used to get in dual supply, but only thing is I have derived VEE in terms of VBB from VCC, right? तो देखो दोनों इक्वेशन सेम है, कोई फर्क नहीं है. फाइनली तो आपको एमिटर करंट को टारगेट करना है, तो आप वो ड्यूअल सप्लाई से भी कर सकते थे. वही चीज हमने सिंगल सप्लाई से प्रूव कर दी. The same thing we have proved with single supply. So with single supply, you can get the same emitter current what you used to get with dual supply. So now your first problem is completely solved. आपका जो first problem था dual supply का, भाई कोई कोई जगह ऐसी होती है कि वहां पे negative supply available नहीं होता है. I don't want to let's say involve negative supply in my system. So in that condition, you can still continue over here. But one thing we have to observe in this circuit कि यहाँ पे collector potential, base potential, emitter potential, everything is different. Everything is lifted. देखो base का potential क्या आ गया? VBB minus IB/RB. emitter का potential भी क्या आ गया? VB minus VBEQ. Collector potential is what? VCC minus ICRC. So everything is different. Everything is lifted. Right? Nothing is common. इसमें कुछ common नहीं है. This is still not like a common emitter. ये common emitter category में भी नहीं है, ये common base category में भी अभी नहीं है, right? You can't say anything whether it is common emitter or common base. Fine. यहाँ से भी हम आगे बढ़ेंगे कि इसको हमें common emitter बनाना है. But before I make it to common emitter, let us take one example. So we would like to take an example for this concept कि ये जो R1 R2 जो है उसको मैं कैसे compute करूंगा. So now I would like to focus on that, right? So now I would like to focus on this example, and we would like to solve this example so that we get a confidence कि भाई नहीं R1 R2 वो सब कैसे compute आप करोगे, right? So the data is VCC is plus 10 volt, VCC आपका plus 10 है, VCB आपका plus 5 है, कलेक्टर बेस वोल्टेज दे दिया है, कलेक्टर करंट 1 मिली एम्पियर का चाहिए, कलेक्टर करंट इज 1 मिली एम्पियर, अल्फा दिया है 0.995, अल्फा इज 0.995, VBEQ बेस एमीटर वोल्टेज आपको दिया है 0.6 वोल्ट. तो यू डिजाइन अ नेटवर्क. व्हाट इज योर क्वेश्चन? क्वेश्चन इज design a voltage divider bias for given condition. आपको ये जो कंडीशन दी है उसके लिए आप वोल्टेज डिवाइडर बायस को सॉल्व करो. दैट इज व्हाट इज योर क्वेश्चन, राइट? सो लेट अस स्टार्ट दिस. वेरी सिंपल. दिस इज वेरी सिंपल एग्जांपल, राइट? तो अभी इसको हमें सॉल्व करना है. तो सबसे पहले क्या करने का, सबसे वेरी फर्स्ट टास्क is to draw the circuit. सबसे पहले आप सर्किट को ड्रॉ कर दो. तो if I draw the circuit, let us say I have RC, there is a transistor, there is a RE and ground, right? यहाँ पे VCC है 10 वोल्ट. We have VCC. तो ये 10 वोल्ट कहाँ से आया? यहाँ पे एक जो बैटरी है उसी से हमें 10 वोल्ट यहाँ पे मिल गया. तो दिस इज योर VCC हैविंग मैग्नीट्यूड ऑफ +10. आपको यहाँ पे RTH और वो फाइंड करना है RB एंड VBB. दिस इज व्हाट यू आर सपोज टू फाइंड. कुछ कंडीशंस दी है. कंडीशंस क्या दी है? VCC इज 10, VCB तो ये है C, ये है B. सो दिस वोल्टेज इज VCB. ये कितना दिया है? 5 वोल्ट. दिस इज VCB वोल्टेज. VCB इज गिवन एज 5. बेस एमीटर वोल्टेज भी दिया है. ये कितना दिया है? 0.6. RE का वैल्यू भी पता नहीं है, RC का वैल्यू भी पता नहीं है, RB भी नहीं पता है, VB भी नहीं पता है. ये सब कंप्यूट करना है. कलेक्टर करंट दिया है 1 मिली एम्पियर का. दैट्स इट. सो व्हाट वी डू, as alpha is 0.995, beta is 199. So I can roughly say IC is approximately IE. Emitter current भी मैं 1 milliampere ही ले लूंगा. I will consider emitter current as 1 milliampere. So emitter current is also considered to be 1 milliampere. तो देखो आपको सभी वोल्टेजेस दिया है. अभी आपको क्या करना है? देखो कलेक्टर टू बेस वोल्टेज है 5, बेस टू एमीटर वोल्टेज है 0.6. सो कैन आई से दैट वोल्टेज बिटवीन कलेक्टर टू एमीटर इज 5.6? कैन आई राइट लाइक दिस? कलेक्टर टू बेस इज 5, बेस टू एमीटर इज 0.6, then collector to emitter is 0.6. Can I write like this? Yes or no? Is it correct or not? Yes, correct. Once you know that, you know the current through RC, which is IC, 1 milliampere. You know the current through RE, which is also 1 milliampere. So now what you do, you write Kirchhoff's voltage law in this loop. तो ये जो लूप है जहां पे मैं यहाँ पे ये सर्कल कर रहा हूं, ये लूप में you write KVL. So write Kirchhoff's voltage law in collector emitter loop. तो कलेक्टर एमीटर लूप में आपको ये लिखना है. मैं अभी इसको हटा देता हूं टू अवॉइड कंफ्यूजन. राइट? तो कैसे लिखेंगे? VCC माइनस ICRC माइनस VCE माइनस IERE इक्वल टू 0, है ना? 5.6 इज व्हाट? VCE. अभी मैंने वेरिएबल्स में लिखा है, अभी आप नंबर्स कर दो. VCC कितना है? 10. IC कितना है? 1 मिली. सो यू हैव 1 मिली ओवर हियर. सो 1 into 10 to the power minus 3 into RC. VCE कितना है? 5.6. IE भी हमने 1 मिली लिया है, तो 1 into 10 to the power minus 3. एंड RE वो अभी नहीं पता है. तो ये इक्वेशन को सॉल्व करो एंड फाइंड आउट अ कॉम्बिनेशन ऑफ RC प्लस RE. RC प्लस RE का एक कॉम्बिनेशन फाइंड करो. यहाँ पे फाइंड आउट अ कॉम्बिनेशन ऑफ RC प्लस RE. 10 minus 5.6 आएगा. 10 minus 5.6 4.4 वोल्ट. 4.4 वोल्ट डिवाइडेड बाय 1 मिली. So milli becomes kilo. So RC plus RE is 4.4 kilo ohm, right? RC plus RE is 4.4 kilo ohm. यहां तक सबको समझ में आया? Are you getting up to this? Okay. So from tomorrow we start from this point. Tomorrow I will start from this point because still there is some time required. So I don't want to take that time because already it's 11. So I stop at this, and from on tomorrow we start from this point where RC plus RE is 4.4 K, and then we will solve it further. Okay, so let us end the session now.